So today we'll talk about how the human ear is working, and I'll try to make some inferences for how you can imagine the ear as being very much like a microphone. So the basic question we want to try and answer today is we know how sound is created. Vibrating things cause sound. We know how sound propagates. It's a longitudinal wave, molecules bumping into each other. This means that areas of compression and rarefaction are moving, and while the molecules themselves in the air don't really move very far. Finally, when ear arrives at our ear, I just said when sound arrives at our ear, how do we hear it? How does that actually work? So I want to review just a few things first. One of them is about our losing of our ability to hear sounds, and you can see here there's a few different examples. These numbers over here on the right mean what age you are, and the hearing loss means that compared with a perfect person, whatever that means, that you can see that the higher frequencies, there's a drop in the sensitivity. So you can think of it as this would be like wearing earplugs. Remember, we've done some earplugs problems where, like, for example, if you wear earplugs that block all frequencies and take it down, say 20 dB, then that means that you are suppressing the sounds. So it's basically you're getting 100 times less intensity getting to your ears. Now this is a little bit different because this is actually talking about as you age, then which frequencies will be more suppressed. So let's take a couple examples. So at 25, you can read across here, say for some of the highest frequencies at like 6 kilohertz, you can see that that you've lost 6 dB. That means that your sensitivity has gone down by a factor of 4. If you go down to 55, you can see that a woman at 55 years old is going to have a 12 dB loss. That means a little bit more than a factor of 10 at this high frequency. Now, if you're talking about lower frequencies, it looks like it's not actually that much of a hearing loss at all, actually. So you can see that it's maybe just 3 dB, so it's a factor of 2. So twice as much intensity would be needed to hear it at the same level. So the lower frequencies you can see here do not experience very much losses. However, if you're a 55-year-old male, you can see that you may not even be able to hear 6 kilohertz frequencies. Now these are pretty high frequencies, right? But most of the frequencies that are relevant for hearing my voice are going to be within the, say, 200 hertz up to maybe 1 or 1.5 kilohertz range. That'll be normal for hearing human voices, right? So you can see that that doesn't change much, but the very, very high frequencies, a 55-year-old male is not going to hear as well. And so you can see a suppression of 30 dB at, say, around 4 kilohertz or 5 kilohertz is going to mean a factor of 1,000 loss in intensity. So that means that one of the sort of takeaways here is that you can see that men will lose their hearing in the high frequency range a lot faster, or a lot stronger compared with females. So let's try a problem together. This is one that we've probably seen before. Go ahead and pause this and see if you can work this one out. Alright, so we're trying to figure out by how many dBs does the sound intensity level increase when 4 trombones play together compared with 1. So to do this, we can use our sound intensity level formula here, which is 10 times the log of the ratio of the intensities. And when we do that, we'll see that it's 10 times the log of 4 divided by 1, which is 6 dB. You might also look in your lookup table that we've gone over a few times, which is basically saying it's doing these calculations, but just sort of putting it into a little chart format. And you can see that a 3 dB increase is a factor of 2. Another 3 dB increase is another factor of 2, meaning a factor of 4 in intensity. And let's say you went up 9 dB, that would be 2 times 2 times 2, so that would be a factor of 8 in intensity. So anyway, we have here 10 times the log of 4 compared with 1, and we've gone up by 6 dB. Just as an example, just since we're here, kind of thinking about these topics here, I will say, what if, for example, one trombone playing was at 50 dB, right? So then if we had four trombones, that's actually 4 times the original intensity. So let's say this is some I naught is the intensity. 4 I naught is going to be 6 dB higher, so that would be at 56 dB. As an extension, what if I were to say, well, actually, what if I had 8 trombones? So 8 trombones would be 8 times the original intensity, or it would be, you could think of it as being 2 times the 4, right? And so every time you go up by a factor of 2, that's like plus 3 dB. This one right here we know is already 56 dB because we worked that out from up here. So in other words, if I had 8 times the original intensity, I can put this together and say that this is 59 dB for 8 trombones. So this is how we do this kind of dB calculations. I just wanted to remind, it's good to keep getting practice with how this works. Let's continue on. So is loudness a physical quantity and measured using the dB scale? Well, if you've been reading the book and you've been thinking about this one, you realize that there's a distinction here. So I would say the answer, let's see, I guess I don't have a way to make the animations go, but I would say false. So you can look up the slides on your own to see the answer to that. I would say that loudness is measured in something called phones, P-H-O-N-S, and it is something that we actually have to use a lookup table to figure out. That we actually can't just look at we can't just measure with some device and know this as a physical quantity. Instead, you might think of it as being a brain-body quantity, which is something we can still quantify. So in that sense, it's kind of physical, but it's dependent on a person. And so in our discussions, we'll talk about kind of the archetype person or a typical person. Everybody's going to be a little bit different in terms of how they perceive loudness. So I would consider loudness as being a perception, whereas intensity is a physical quantity. All right. So if the volume of an amplifier is increased such that the quiet music increases by a factor of 10,000 in intensity, so that, in other words, would be how many dB up? It would be 40 dB up. How will the quality of the sound change? Give you a moment to look over the options. So hopefully you notice that the bass frequency range will sound too loud, and maybe even that's been something of your experience here. And to relate that to a picture where we can actually begin to understand this more fluidly, let's take a look at this equal loudness contours here. So it's a bit like how do you say, altitude map, where as you cross these lines here, you're going up and up in higher phones. So you can see here that as we go up to higher levels here, you can see that 20 dB, 40, 60, 80, 100, and 120, these are all kind of defined at 1,000 hertz or 1 kilohertz, which is in the audible range. But as I move up here, so for example, if I change the sound intensity level up, say from 20 dB up to 40 dB, you might notice that that if all the frequencies increased in the same way, that we would actually have that they would be changing in their perception of how loud they are in different ways for different frequencies. So I stepped out, so I just coming back in. the way we might look at this previous question here, the quality of the sound changing. The answer here was that the bass frequency will sound too loud. Now, this might not seem correct, because if you look at like a bass frequency, for example, that's just at the threshold of hearing, that looks like that is a 70, let's say, I don't know, let's call it a 75 dB sound intensity level, is just barely audible, right? And you might be like, all right, well, let's say, what if it was a 75 dB sound intensity level? What does that sound like, let's say, at 1,000 hertz? You say, well, wait a second, it sounds like it's like 70 or 75 phones. So that's kind of weird. Remember that these contour lines represent phones, the perception of loudness. But if you think about it in the analogy of a contour map, like a mountain, you might notice that increasing, let's say, 40 dB here causes you to cross 3 or 4 contour lines, whereas going up 40 dB here only causes you to cross about 2 lines. So the idea is that the loudness in the bass is going to rise much sharper, much faster in comparison with the treble frequencies. Okay, now let's move on to talking about the human ear. So this is kind of a sort of cutout picture to show you, well, what does it look like, these different parts of the ear. So this pinna is just meaning your outer ear. And then this would be if we were to remove all of the cartilage and bone to see what's going on underneath the surface here. You could actually see that there's a canal, and then there's looks like some pretty complex pieces in here. And we're going to take a look at these parts in here and try to make some sense of it. So if we go a little bit deeper inside, we can kind of get a blow up here, and we can see that there's a part in here which is the malleus, incus, and stapes, and so you can read about this in the text. I'll also post a couple of video links that will do some kind of animations showing you more specifically what's going on in here. You can think of the eardrum as basically moving back and forth, and then you have these other 3 parts in here which make up what is called the ossicles, that they are moving together, and they are amplifying the small vibrations in this drum are then being moved, and finally changing that to remember that this whole thing is vibrating all the time, and then it's sending these vibrations down the cochlea, and then we'll talk about what happens actually there. Ultimately, the idea is that it's sending electrical signals to your brain. So, okay, why is there a middle ear? What do you think? Is it to provide some amplification? Is it to couple the pressure waves to vibrations in the cochlea? Is it to protect the inner ear? Or is it to maintain the tympanic membrane, or the eardrum, in a proper pressure equilibrium? Or is it all of those? Well, again, we'll take a look at the answer is all of these, actually. And so it's interesting that this middle ear, right, which is this collection of all these parts in here, they serve a lot of purposes. And so you can imagine that if some high pressure waves come in, that they actually they do amplify the pressure waves. But interestingly, if there's too much pressure, it actually this acts as kind of like a blocking place that actually will protect your inner ear from being damaged if things are too loud. So it's quite a lot of function that's happening in there. It's really amazing that we humans, and many other animals for that matter, have evolved to have such complex biological features. And so one thing that I want to do is, since this is a physics class and not an anatomy class, is to try and relate those functions, thinking about the physics that's involved. So if we were to take this cochlea here, that's the little snail-looking thing over here, and if we were to sort of unwrap it, or sorry, first I'll do it like this. I'll take a slice across it, and you can see that there's a lot of things going on in there. There's these little hairs inside, and we'll zoom on those in a second. And then what it's wrapped around is this auditory nerve, which is going to ultimately send some signals to your brain. Let's zoom in on one of these little things here and see what it looks like. So in other words, the scale kind of gives you an idea. It's a millimeter, so it's a couple of millimeters, a little snail thing. And if we zoom in even more, you can see that there's going to be sound propagating through these chambers, sound waves, and then these little hairs are going to be excited, and ultimately these are connected to the nerves, which then sends down through this cable of auditory nerves. So this little nerve right here is the same thing as this little nerve right here. It's going out into the little bundle and sending out information to the brain. Now let's unwrap this cochlea. So unwrap the snail. Maybe you could imagine it's going to look something like this. So your cochlea is unrolled in this picture here. So it is normally looking like a snail, but if you unrolled it, then you would see something like this. So here's our tympanic membrane. It's the malleus, incus to the stapes. These then stimulate pressure waves that move through the cochlear fluid in and ultimately stimulate these hair follicles and will send information down the auditory nerve. I'd like to recommend watching this YouTube link. I'm just going to open it ever so briefly here. We won't watch the whole video in this YouTube video. Wow, a YouTube video in a YouTube video. I have to think about that. But rather, I'm going to place this as a link, and you can please watch this video.
Millions of people suffer from hair loss and don't have a reliable.
And if you have hair loss questions, okay, skip ad. So here's a discussion of what's happening inside the ear. It's a very nice little video, and you can see that they have really nice animations and showing you really in 3 dimensions what is really going on inside of here. So here's the cochlea. Here they're showing you the hair follicles. Please watch this video and really get a sense for what's actually happening inside here. But in any case, these are some of the terms that I'd like for you to know about the ear. And let's practice here. What are the small bones that transfer vibrations from the eardrum to the oval window? So if you've studied the book a little bit, you'll know that it is indeed the ossicles. That is these 3 red ones right here, malleus, incus, and the stapes. Okay, so we'll have some other pictures here. So you're seeing that I'm showing you different, like a variety of different, pictures of more or less the same thing, but I'm emphasizing different details in each slide. And so here's again the malleus, incus, stapes, the ossicles. And then what's being emphasized in this slide here is this partially unrolled ossicles. But what's really interesting is that the high frequencies in the cochlea, they actually stimulate the hair follicles that are earlier on in the cochlea, whereas the lower frequencies stimulate the ones that are all the way at the end. It's pretty weird, but that's how it works. And so in some sense, remember the spectrograms, like the lower frequencies and then the higher frequencies, your cochlea actually performs this function based on where the sound waves are stimulating the follicles. It actually then, your brain then interprets the sound or the perception of the sound based on how far the sound made it into the cochlea. Or maybe another way to look at it is which hair follicles were stimulated. We might even, if we were to go a step further, we might say, well, perhaps there's some standing waves that happen in this cochlea, but we won't do that at the moment. But that's the idea, is that different hair follicles are being stimulated, and that is actually telling you then what frequencies you're hearing. So here's some kind of images here. These were taken with electron microscopes, and you can actually kind of see the shape. This is a cochlea that was cut in half, a normal cochlea, and you can see a zoom in of a damaged cochlea that has the hair follicles that are in there are not as consistent, and some of them are shorter. As you can see that this is what a normal cochlea would look like, but then the damaged one actually is more sparse, and so this would be somebody who might be hard of hearing. So lastly, I'm going to show you just some pictures here of the distance from the stapes. Remember, that's the thing that's transducing these waves that are traveling in down through the cochlea. The further they make it, so the ones that are maybe, let's say, 30 millimeters in, it would be 200 hertz, and maybe the ones that are closer to the stapes maybe let's say around 20 millimeters in, it's going to register as 1600 hertz. And you can see that it's not a very sharp spike, so your brain has to probably do a lot of different kinds of processing in order to figure out exactly what's really going on. But in other words, what your cochlea can do is it's sensing different frequencies based on where those sounds stimulate hair follicles. And then lastly, I'll show you a picture that might look surprisingly like a microphone, for example, something that senses sound, right? You're speaking into it. It has a place where it goes in, and it has something that transduces the sound, and then finally something that sends out the signal. That would be just the same as the cable on a microphone sending information to an amplifier, for example. So your body is a very interesting system that can create electrical signals that your brain interprets based on sound waves. Thank you for watching the video, and please take a look at the video links below for more animation. And that is it for now.